Hi, and welcome to this video. Today we're going to be talking about how to optimize your tolerance stack-ups by design, so geometry rather than calculation. Marcus, what's on the menu for today?
So we will go through 3 simple principles for how to optimize your stack and your design. We'll go through them one by one, and then with an extra little prerequisite, the most overlooked thing in engineering perhaps. So a small cliffhanger.
Good. I brought a simplified example out from the real world, so tell me, how would you optimize this one?
Depends on what you say the requirements are.
All right. Well, in this case, my key functional requirement is the alignment between the button and the cutout on the lid for the button.
Okay. So let's break it down. The example here consists of a cover, a PCB, and a frame. And the PCB is housed in the frame, and then we have the cover on top. So very classic construction here.
So, object is clear. What are the 3 principles?
There's 3 simple rules, but before we're jumping into to the rules, there's actually a check that we need to make before, and we need to check for if the design is overconstrained.
Okay, a plot twist from the get-go. All right, why is this?
So in the main viewer here in the application, you will see a representation of the interface between the lid and the base. And if we X-ray it and scan it, we can go all the way to actually hide the geometry. You will see that there's a lot of geometry that is highlighting here that is not green. What is highlighted is the functional surface area. So this is everything that's not green is actually ambiguous. So we don't know what is positioning what. So, and the same goes for the PCB. So if we make the parts transparent, we are seeing that there's a big surface area in the bottom that's unclear. That's because we have a big plane, so there could be unevenness that will misposition the PCB. And there's 2 pins. So in this case, we don't know, this is perhaps the most easy to understand, we don't know which of these pins is positioning in the X direction. So your question was, how do we make sure to optimize this? And the point here is that we don't know which of these features is controlling the position of these parts relative to each other. So there's multiple paths that we need to control.
Okay, yeah, difficult to predict. So, so we established the paths are not predictable. How do we solve this? All right.
So we'll go into Creo. And what you see here first, this is our original CAD model. And now we will try to optimize it so there's no overconstraints. So from the outside view here, you'll see that a little bit has changed. So these positioning features, they are grabbing on the outside. Before there were 2, now there's only 1 here.
So now you have 1 set of surfaces controlling the position in that direction.
Exactly.
All right.
And if we look under the hood, then it's the same story for the PCB. So there's added a little bit of clearance here to the right pin. So we have an oblong hole. Now we know exactly that it's the left pin that is doing the positioning.
All right.
And again, if we dig a little deeper, then you also saw that there was a big plane before. Now there's actually only just 3 support areas that is defining a plane.
All right. So looking at the contact model from before, we could see that there were these sort of problems or unpredictable contacts. With this model, could we do the same?
Yeah. Okay, so let's import an iteration. So now the changes from the CAD model is updated, and what we see here, suddenly there's no red flags. Everything is green except for the point of interest, which is between the lid and the PCB. We want to make sure that the highlighted red surface here, that there's no chance of that these can conflict. So the system is warning us that there might be a potential contact here, and what we now want to prove with the tolerance stack is that the clearance here is perfect. If we look again at the lid, or the constraint between the lid and the base, see everything is green, and we can X-ray it, and you will see that all the contact surfaces, they are now green. I can even hide the geometry and you will be able to see all the functional surfaces here. and their functionality. You can click on each surface, and then you can, and the software will tell you what is that surface actually doing. Let's take a more simple example with the PCB.
So this was the pin and the oblong hole orientation. Yeah.
Exactly. So what you'll see here is that, again, no overconstraints. And if we X-ray it or make the parts transparent, then there's a very clear contact scheme in this case.
Yeah, this looks like sort of the classic 3-2-1 locator scheme.
Exactly. So I can take you through this. So we'll have 3 points. This one, and this one. That's defining a plane.
Mm-hmm.
Then we'll have a set of 2 features here. That is defining locking the rotation.
Mm-hmm.
And then we'll have a last one that is defining the translation. So here it's crystal clear what each surface in the design is doing.
And you don't have to worry about sort of conflicting paths or which geometry is actually controlling the stack path that you're going to go through.
Exactly.
All right. Well, in this case, so we have a predictable design. We have a clear datum scheme or locator scheme. So I guess now we're ready to calculate.
Now we're ready to calculate. So,
Awesome.
so let me show you an example. We have cheated a little bit and pre-cooked. We have set up the tolerance stack.
Yes.
On the right side of the application, you will see the canvas where the stack is documented.
Okay. And so my requirement was about the placement of the button versus the cutout in the lid. We never wanted to interfere. You were showing that in the 3D model from before. What about the upper requirement? What is the limit for our performance here?
So let's say that around 0.4 is the upper specification limit. We have around 88% that is failing. So we only have a yield around 12.45.
All right. So in this case, there's definitely a need for optimization. All right. So let's talk about the principles.
The first trick or the first principle is to shorten the tolerance stack.
Mm-hmm.
And that means that either we can reduce the number of parts or the number of parameters in the stack. So it sounds very simple, but it's actually harder to do in practice.
Okay. So what would that mean in real life for this example?
Yeah. So we could cheat a little bit, and we could mount the PCB directly on the cover.
Mm-hmm.
That will make a very, very short tolerance stack where we are short-circuiting the base. We can just throw it away and only worry about the fit between the PCB and the cover.
All right. But I guess that would make it too easy in this example. So let's say that that's not allowed.
So principle number 2, it's about maximizing the distances. So as you saw in this case here, the lid is very poorly oriented. There's no overconstraints, but perhaps they're not placed optimal. So let's go and have a look in the CAD model of how we can solve it. So what you see here is iteration number 2, the version without any overconstraints, but we want to maximize the distances. So let's swap and toggle a little bit back and forth so you can see the differences. So what is happening here is that we are changing the placement of these features. So they have a much wider fit. So if we look under the hood, it's the same principle that we try to put the positioning features as far away from each other as possible. So let's jump into the RD8 software and jump to iteration number 3. And we see that everything is still green. So no changes in the constraint.
Yes.
So we can dig into the details and see that the features have now placed, but they are still green.
All right. I'll take your word for it, but nice that we can sort of that we can keep checks and balances as we evolve the design.
Jump to the third principle, say if we can improve the design even further. So principle number 3 is about optimizing fits. So there's 2 set of sub rules for this. So the first one, if we can use smaller local features,
Mm-hmm.
and the other thing is if we can eliminate play. So how does that look in real life?
I'm sensing you have a model ready.
Okay. So let's have a look at the update from version 3 to version 4.
Mm-hmm.
So that in this case we have wide fits, we have maximized them, but we have actually a large span a great width from here to here.
So you're saying that the sort of the controlling surface pairs are spanning the entire interface for all of our positioning features.
Exactly. So they are as wide as they can be. So if you want to try to apply the third rule, it's a very good example. So let's see if we can get them down to more small local fits. What it actually means is that we have changed the interfaces a bit. So instead of being some like kind of hooks or features that constraints on the outside of the box, we're actually making small indents or grooves in the design. So now it features 3 constraining features here.
I guess if you recall your tolerance tables, then you know smaller dimensions, you can allocate a smaller tolerance without pushing your capability.
Exactly.
All right.
And it's the same trick that is applied for the PCB. Before we saw that we actually only had 2 pins, but now we're having 3. And that's a little bit looking back to the first principle. Features that is positioning in the X direction, they're actually placed as close to the button as possible.
Okay, so this makes sense. We localized to get sort of better tolerances without pushing the capability. You have everything centered on a one singular reference instead of having offsets. I get that as well, fewer parameters. But then again, let's circle back. Do we still have a predictable design? Now you've introduced new geometry.
So we'll go to iteration 4, and whoo, luckily everything is still green. But again, the locating scheme have changed a bit. So again, we can drill down, and now the X constraining feature is moved to the center.
Mm-hmm.
And let's say that the rotation locks, they are placed here. So same functionality, just in a different kind of...
So still a 3-2-1 locator scheme, but now arranged differently in the interface.
Exactly. It's the same for the PCB. If we drill down, the same kind of locating scheme. I'll hide the PCB here so you can see the green surfaces. The geometry, again, has changed slightly. The X constraint here in the center. And we have the rotational lock placed here.
Makes sense, even if it looks contradictory. I'm sure you'll get some comments on this design later down the line. Okay, so far so good, but you had sort of an extension to principle 3, which was no play or 0 clearance. If I decode this model correctly, then you still have a little bit of play in all of your localized fits.
Yeah. So let's go into the CAD model to see how we can optimize this to eliminate any clearances.
All right.
So what you will see here, when we're going from iteration number 4 to iteration number 5, is that we introduce these small cutouts, and we actually introduce a small overlap here in the geometry. So it's a small, like a compliant mechanism, or you can also call it a small feature with a little bit of flexibility that pushes the lid to the left side in this view. At the same time, you see that the datum plane have changed. Instead of just being in the center, then the datum plane is actually moved to the center of the
yeah, so you went from symmetrical centering to now you actually have sort of your contacts one-sided on the same line.
If we check in the RD8 software, here you'll see iteration 4 with a little bit of clearance in the center.
Mm-hmm.
And here you see the update with the shifted geometry. So the datum plane is exactly in the center of the pin. So I can toggle a little back and forth here. Here you'll see the updated tolerance calculation and the benefits of this. So recall the first stack, we have a lot of failing samples. And we also see that we have 9 parameters that we need to keep in control. If we look at the latest version, latest update, you'll see now that we have removed the number of parameters to only 4. And
yeah, I think I can see from at least from the visualization alone that sort of the path is simpler, but obviously the performance is better as well.
Exactly. So now we have 0 failing items. All of these parts pass the requirement. Mm-hmm. So if we take a look at the results in the initial non-optimized design, we have around a window of variation of around plus minus 0.5. And in the optimized scenario, we have a much better performance. There's a variation of around plus minus 0.12.
And you pulled this off by optimizing the design so that you can say the tolerances or the tolerance capability level, the tolerance grades and classes are the same as before.
Exactly. No changes to production requirements at all. The same assumptions applied before and after. So it's very powerful, these three simple rules. They're very simple, but you will actually gain a lot of impact. So in this design, we're gaining almost 80% more accuracy just by placing the features very smart.
Very nice. And I guess you could say sort of, if we take these results, extrapolate them downstream, so the design leaves me as a designer, now moves further down the line. For parameters, I guess I can make friends with metrology or with my quality people. They have less information to verify and control. If I'm in doubt or if I need to change something at some point, then again, it's much more traceable. But perhaps let's take a step back and recap the process to finish off.
Let's go through the steps applied one by one. So the first step from going from iteration 1 to iteration 2 is to eliminate all overconstraints. The next step was to say, can we maximize the distances? Can we space features as far apart as we can possibly? Step number 4 is again making small localized fits. And the same for principle number 3 was to eliminate any play. There was also this principle number 1 where we could short circuit the tolerance stacks and say if we can eliminate any parts, let's do that. We're not allowed to apply this in this case.
Would have made this video way too short.
Exactly. So here you see that example where we hide the base, then we are seeing that the PCB is mounted directly onto the copper.
All right. Well, good recap. Thank you for the principles. Thank you for highlighting what happens if you're not in control of your constraints. Amazing what you can do optimizing by design.
Do you know the quality of your designs? We do.